I will begin with a word of prayer. It's bouncing, yeah? Okay. Dearly Father, we thank you again, Lord, for this opportunity just to meet together and study your creation. And we again just thank you, Lord, that we can have your righteousness and not our own, because our own righteousness is worthless, but yours is worthwhile. And we thank you for that, Lord. Just help us and guide this class today, Lord. In your name I pray. Amen. All right. Determinants. What's the deal with determinants? So, well, determinants have been studied for a while now. I mean, there's a vast literature of determinants stemming back from the 19th century. In fact, much more of the focus of linear algebra used to be on determinants. And here, on the other hand, I'll spend 2 days telling you about determinants and what we have to say about determinants. And the basic idea is this, is it should somehow describe, well, let's say quantify the signed volume of an n pipette. So let me tell you what an n pipette is. P generated by, say, V1, V2, ... Vn. It's going to be something like C1 V1 plus C2 V2 plus ... plus Cn Vn, such that, all right, so all possible linear combinations of these vectors V1 through Vn and I'll keep it real in here, all right? But the determinant I'm defining equally well makes sense for a commutative ring with identity. But I don't have so much geometric to say there, okay? So I'm going to focus on Rn where I can say things geometrically without apology. So this is an n pipette, or sometimes you might say parallel n pipette, or provided those constants are between 0 and 1, and well, oh, actually I should just say C1 plus C2 plus ... plus Cn less than or equal to 1. And the Ci's are greater than or equal to 0. Let's just look at n equals to 2. n equals to 2. So n equals to 2, this would be like V1, this would be V2, all right? And sorry, I'm looking for something here. Right quick. Where'd you go? Oh. Curses. And so the parallel pipette that's defined by V1 and V2 would be this right here would be like V1 plus V2. I don't think my condition's quite right. Because here I've got C1 and C2 are both what? Both 1. So the sum of like C1 plus C2 is 2. So my condition's not quite right here. All right, so I'm going to let you guys think about that. I'll think about it too, but I think maybe at least at the moment I've got to. This isn't quite right. Not quite.
What's wrong with what you had before, having each one of them?
Well, I do think that's, I mean, yeah, I do want that. 0 less than or equal to Ci less than or equal to 1. Yeah. I think that's all I want. I just want 0 less than Ci less than 1 for each one. So let's just say that. So what that does is it allows you to take a copy of between 0 and 1 worth of V1, between 0 and 1 versus V2, and you just build all possible linear combinations, this gives you an n pipette. I mean, n equals to 2 is just a parallelogram, right? If you have 3, all right, like that, and I for the purpose of my my artistry, I put the V3 over here. Then if you look at all possible, linear combinations of V1, V2, and V3, where you're taking at most one copy of each one, it'll fill out a parallel pipette, as it's sometimes called. All right. Now, so what should the signed I omitted an important thing right there. I meant to say signed n volume. So like a 2 volume is what? Is area. A 3 volume is, well, what we usually call volume, okay? What's a 4 volume? You could call it a hypervolume, 5 volume, hypervolume, but that would be the next notion of a volume past 3, past what we're able to actually sort of visualize, namely area and regular volume, right? Okay, so the question then is, how do you define, we want to define some sort of function which calculates the signed volume of an n pipette. So what are some guidelines? Well, one guideline I would think would be if we look at the parallel pipette built from E1, E2, all the way out through En, this ought to have, the volume of that, surely it should be 1, right? Like if you think about the unit square, what's the area of the unit square, right? Or what's the volume of the unit cube? You know what it is, right? It's also 1. What else should we expect about this volume function? And I say signed volume because we also have this idea, if you were to reorder any, like if I was to put the ordering of the vectors matters. So if I was to like flip E1 and E2, it would get a -1, all right? So like the order in which you're given the legs to the parallel pipette will matter, all right? If you just switched one pair, it would just change the sign of the sign volume from plus to minus or minus to plus. What else? How about this? If we were to take a leg, if you think about this, if we were looking at the volume of something, say the parallel pipette, which had, say C V1, V2, Vn, and we were to compare that, the volume of parallel pipette with just V1, V2, Vn, what should the relation be between, everything else being the same, if I just take one edge of the parallel pipette and I just scale it by C, what should happen? The volume should scale by C. We know this from the area of a, like a rectangle, length times width. If we take the length and make it C times the length, we get C times the length times width. And the same for the width, right? If we make the width longer, we also multiply. So yeah, we should be able to just say that this is equal to C times the volume. With the understanding, if that C is negative, we've disoriented it. I mean, that'll affect the sign volume. So these ideas, all right, effectively define the determinant to be this signed volume. All right, so the determinant is exactly this. And so here's the definition. The determinant of, if we take the determinant of A, it's the sum I over I1, I2, dot, 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 In equals 1 to n. Bless you. So I'm going to write down a rather horrible formula. You'll forgive me. I1 through In equals 1 to n, and then use a symbol, epsilon, I1, I2, dot, 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 In, and then a, let's see here, column 1, let's say I1, 1, a, I2, 2, a, I, and this defines the determinant in such a way that it will satisfy, it will actually give you back these features. Now here, epsilon I1, I2, dot, 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 In, excuse me, is, I should say, 1, 2, 3, all the way out through n is equal to 1, then any swap of inputs generates a minus. So it's also called the so-called completely antisymmetric symbol. Or sometimes called the Levi-Civita symbol. This is, so one of the things that means is if there's any repeat here, the Levi-Civita symbol is 0. So if I have like epsilon 1, 1, whatever, that's 0. By the way, what should the sign volume of a n pipette be if any of the edges are like parallel? Like what if the picture wasn't this? What if the picture was V1 and V2 are both like on top, just V1 and V2 are both like collinear? What would the area be of that?
We don't have any area.
The area would be 0, right? So if there's any kind of linear dependence amongst the vectors, the edges to the n pipette, we should expect that should be 0. That's part of this. Let me give you what it looks like at n equals to 2. n equals to 2. We have epsilon 1, 2 equals to 1. We have epsilon 2, 1 is minus 1. All right? Now, epsilon 1, 1 equals to epsilon 2, 2. Those are 0. So if we calculate the determinant of a 2 by 2 matrix, according to this formula, it's the sum over I and j equals 1 to 2, epsilon ij, a I1, a j2. So I've used I1 as I and I2 as j here. I don't need, I sub j. So what we've got then is epsilon 1, 1, a1, a2, 2, excuse me, a1, 2, plus epsilon 1, 2, a1, a2, 2, plus epsilon 2, 1, a2, 1, a1, 2, plus epsilon 2, 2, a2, 1, a2, 2. There are 4 terms in principle. So what? Well, again, by definition, 1, 1 is 0, 2, 2 is 0, 1, 2 is by definition 1. And so what we're looking at is a1, 1, a2, 2, minus a2, 1, a1, 2. And you might recognize that from your other coursework, right? The determinant of the matrix a1, 1, a1, 2, a2, 1, a2, 2 is in fact that. Yes, sir?
Why is E11 and E22 equal to 0?
By definition. By definition. N equals to 3. We have the determinant of a equals to the sum ijk, goes from 1 to 3, of epsilon ijk, a I1, a j2, a k3. For the Levi-Civita symbol and 3 symbols, we have epsilon 1, 2, 3 by definition is 1. All right. And that's equal to epsilon 2, 3, 1. And that's also equal to epsilon 3, 1, 2. On the other hand, epsilon 2, 1, 3 is equal to minus 1, as is epsilon 1, 1, 3, 2, and epsilon 3, 2, 1. So there are 3 pluses, there are 3 minuses. Those are the 6 distinct triples possible with 3 things. And all the other 27, I mean, there's 27 possible things you could think about with ijk. ijk taking on values from 1 to 3, right? 3 to the 3 is 27. The other 21 of them are automatically 0, because like epsilon 1, 1, whatever is 0. If there's a repeated index, it's automatically 0 by definition of the symbol. And so, long story short, we have epsilon 1, 2, 3, a 1, 1, a 2, 2, a 3, 3, plus epsilon 2, 3, 1, a 2, 1, a 3, 2, a 1, 3, plus epsilon 3, 1, 2, a 3, 1, a 1, 2, a 2, 3, and so forth. There are six terms, all right? Epsilon 2, 1, 3, a 2, 1, a 1, 2, a 3, 3, and epsilon 1, 3, 2, a 1, 1, a 3, 2, a 2, 3. And I think I'm finally to the last one here. I shouldn't have signed up for this. Let's see here, 3, 1, 2, 2, and finally 1, 3. All right, great. So that gives us a 1, 1, a 2, 2, a 3, 3, plus a 2, 1, a 3, 2, a 1, 3, plus a 3, 1, a 1, 2, a 2, 3. And the last 3 are minuses. So minus a 2, 1, a 1, 2, a 3, 3, minus a 1, 1, a 3, 2, a 2, 3, minus a 3, 1, a 2, 2, a 1, 3. Now, let's see if we can't organize those terms to make it something that perhaps we've been taught in another course. Or maybe not, I don't know. A11, A12, A13, A21, A22, A23, A31, A32, A33. So this is the determinant of a 3 by 3 matrix. Perhaps you've been taught to expand by minors. We can, across the top row, pick off the coefficients of the top row and write them down. Let's see if I can do it. So this should be like A11, all right? And then there's going to be A22, A33 minus A23, A32. Let me just take a second to find those terms from my definition. So that's this one. Where's my A11 over here? Right here. The next thing in the expansion, you do minus A12, and I'll use a different color here. So notice A1, where's A12? There's one right here. Where else is one right here? So we got A12, A31, A23, minus A21, A33. So let me point out what we're looking at. This is in fact the determinant of what? It's the determinant of the original matrix with the first row and first column crossed out, right? This is this right here. Yes, sir?
I understand that. I just don't understand how you're getting 1 and -1 from E.
The definition of epsilon 1, 2, 3 is that it's 1. If I swap any pair of indices, it generates -1. This defines epsilon.
But how can you switch them up there and it's still equal to 1?
No, these are -1.
No.
The last three are minuses. The first three are pluses. What did I do?
It's still -1.
Where did I do it?
You just maybe.
Like you have E123 and E231 and E312 equal to each other. But
Am I pointing at the wrong one?
at the very top,
Yeah?
those, yeah, you have
Yeah,
those
but-
equal to each other, but the numbers are switched, so how are they equal?
These are by the definition of the epsilon symbol. Look, so 2, 1, 3, from 1, 2, 3, I swapped 1 and 2, so 1 becomes -1. 1, 3, 2, I swapped 2 and 3, so 1 changes to -1. 3, 2, 1, I swapped 1 and 3, so 1, 2, 3 changes to the 1 changes to -1 for these. All of these are obtained from 1, 2, 3 by 2 swaps. So to get from 1, 2, 3 to 2, 3, 1, I have to first swap, I could swap 1 and 2, and then I could swap 2 and 3.
So if you swap it once, it's negative. If
These
you
are-
swap it more than once, it's positive.
If it's an even number of swaps,
If it's an even number of swaps, it's positive.
yeah,
Okay.
yeah. So this one here is the determinant of, what do we got? Oh, there it is. A21, A23, A31, A33. That's not quite right. Did I neglect to take care? I neglected to mind my minuses, right? So if I pull this minus out, that makes this a plus. It makes that a minus, which then would be this. You should recognize this pesky sign as that thing that you were struggling with the cross product in Calculus 3. If you haven't had Calculus 3, my apologies. You were cheated. All right, next up. Of course, color coding, we're looking at this and that, right? That's what's appearing there. And then finally, plus A13, and what do we got? A21, A13 minus A22, A31. This will be the determinant of a, how's it go? Oh yeah, I've messed that up. That's supposed to be what? Say again?
Oh, sorry,
3, 2. So A21, A22, A31, A32. I mean, what I have there should be what we get from crossing out the first row and the third column, if I did it right. Should be this. If I did it right. Let's take a step back here. So I've got my 1, 3, A21, A32. Then over here, I've got my A13, my A22, A31. Bingo. So what I'm pointing out here is known as Laplace's expansion via minors. And what Laplace's expansion by minors states is that you can take any determinant of an n by n matrix and you can expand it as an alternating sum of n determinants of submatrices of n minus 1 by n minus 1 matrices, where you have crossed out the given row and column corresponding to the expansion. So here I expanded across the top row. These are the determinants of the submatrices formed by crossing out, first of all, the first row and first column, second of all, crossing out the first row and second column, and then finally the first row and third column for the last one. This pattern generalizes. You can expand about any row or column. And this is sometimes a good way to calculate determinants. I mean, let me show you a different one. But before I do that, let me just take a moment to talk more, just, concept. So getting back, if we have determinant of vector v1 and vector v2, if that's positive, right? If we have determinant of v1, v2, v3 positive, I actually use these in part to justify the formula for the determinant in my notes. And the long story short of it is simply this: if v1 is like this, and if this determinant's positive, what that means geometrically is to get from v1 to v2, it's a counterclockwise rotation. So v2 would look something like that. I don't know. But the point is, it's a theta. It's counterclockwise if it's positive. If the determinant's negative, that means that the first column is clockwise rotated to get to the second column. If the determinant's 0, they're collinear. This one, what this positive means is if you look at the plane with v1 here and v2 here, and you calculate by the right-hand rule the cross product of v1 and v2, as we learn in Calculus 3, that gives you a vector which is perpendicular, of course, to both of these, right? v1 cross v2. And so in some sense, v1 cross v2, which we could put over here if you like, parallel translating, a la Calculus 3, that defines which way is up. It says that if we look at the plane with vectors v1 and v2 tangent to the plane, the top of the plane is given by v1 cross v2. What this determinant being positive says, it simply says that v3 is on the upper side of the plane. It means that v3 is somewhere up there. So v3, it doesn't have to be perpendicular, of course, but it's somewhere up here. If this was negative, that would mean that v3 is below the plane. That's what the plus or minus means. All right. So that's the sign of the determinant. It has to do with the orientation of the volume. All right. So with that, I mean, I tried to motivate a little bit why we're defining the determinant as we are, in part by these considerations. But so here's an example with numbers. It suppose we were calculating the determinant of 4, well, yeah, fine, 0, 0, 7, 0, 0, 0, 6, 8, 1, 1, 1, 1, 2, 2, 0. It's a 4 by 4 matrix. So let me just, illustrate Laplace's expansion. And so do the bottom row? All right, I guess that might be instructive. So I will expand about the bottom row because I can. All right? So this is going to be 0 times the determinant of whatever, minus 2 times the determinant of something, plus 2 times the determinant of something else, plus 0 times the determinant of who cares. So let me that's the general pattern. So what we do is I got to be careful. It goes like this: plus, minus, minus, plus, minus, plus, minus, 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 plus, minus, plus. So you can, in other words, you put minus 1 to the I plus j as the sign for the Laplace expansion. And so I'm wrong as it stands, because in the 4th row, we end up starting with how's it go? We end up starting with a minus. So this should be minus, plus, minus. All right, getting to it then, we're looking at the determinant of what? Well, the first two we basically think about crossing this and that out, and that leaves us with 4, 0, 0, 0, 8, 1, 7, 1, 1. That 2 is still there. And then I do minus 2 times the determinant of the 3 by 3 obtained by crossing out, I'll do it in green, this one and that one. So I won't write in green, though, because that's nearly unreadable. It's like ghost writing. So we got ourselves a 4, 0, 0, 0, 6, 1, and finally a 7, 1, 1. And then how do we do that? So I recommend for this one, let's expand on the first column. So expanding on the first column gives me 4 times the determinant of 8, 1, 1, 1, and then minus 0 plus 0. See, if I can find a column which is mostly 0 or a row which is mostly 0, I can exploit that to simplify my calculation. All right? And how about this? How about this one? I mean, I guess I should do the same thing, right? Expand on the first column over there to make life easier. So what do we, and I've lost my 4, haven't I? So that gives us 8 times 8 minus 1 minus 8 times 6 minus 1. So the answer is 8 times 7 minus 8 times 5, which I think is 56 minus 40. So the answer is 16. Yeah.
So for the original matrix, I see the word going on the bottom row. When we get into the formula of the 3 by 3 matrices that we're going to expand upon even further, how do we choose that particular 3 by 3 matrix?
That's the 3 by 3 matrix, which results in crossing out. So that 2 is this 2, and what's left is crossing out that second column and the fourth row. It leaves me these.
Oh, I see.
It's always, yeah. Well, it's always what's not there. Yeah.
For the 4x4 matrix, you pick the row on the bottom to expand.
Yep.
But for the 3x3 matrix on the other board, you pick the row on the top.
Yep.
Reason where you choose which one?
Oh, I was illustrating. In fact, this is Laplace's expansion by minor. Says you can expand about any row or column as long as you keep track of the plus minus and expand about the submatrices. Yep.
So how would it have been different if it wasn't the minus 0 plus 0? And you started writing in red.
Oh, it would have made it minus 16, and it would have been wrong. It would have flipped. It would have been plus, minus, plus, minus. It always flips back and forth, plus, minus, plus, minus.
No, I get that. My point is like if you had chosen a different one and it wasn't 400, and so you
Oh.
had like more determinants.
Sure. If I had done that one, it would have been. See, that one starts with a plus. That would have been like plus 0 times that determinant, minus 1 times that determinant, plus still 1. The contrast of 1 and 1 ain't great here. And then minus again 1. Sorry, for example, that was not your question. Okay, what's your question?
Where you started writing in red, where you have 2 times 4 times the determinant of 8, 1, 1, 1, and you have minus 0 plus 0.
Uh-huh.
What if you had chose a different one? Like how
Wouldn't have
would you
mattered.
calculated
Oh,
1
it would-
minus 0 plus 0?
Sure, if I had done that, I would have had 4 times the determinant of 8, 1, 1, 1, plus 0, well, minus 0 times stuff I don't care about, plus 7 times the determinant of 0, 8, 0, 1. Of course, this is just 0, and this is 4 times 8 minus 1, which is, what is that? I don't know. 28? 4 times 7? Which is what we had there. Yeah.
So we could have just been smart and picked the first column.
Indeed, yes, it would have been lazier to pick the first column to start with. Then we would have just had 4 times the determinant of that. That's what we should have done. Right. Indeed. To be lazy, but I was trying to illustrate the expansion rule. Okay, so theorem. A theorem we should think about before I get any further. What was our theorem? A inverse exists if and only if what? Ax equals to 0 if and only if what? X equal to 0, right? But let me just relabel that. AC equal to 0 if and only if C equal to 0. Because if I do that, you can see that that's really C1 column 1 of A plus C2 column 2 of A plus Cn column n of A equal to 0. What is this to say? This is to say that A is invertible. A square matrix is invertible if and only if its columns are what? Linearly independent, right. The simple calculation proves, on the basis of the things we've already done, that a matrix is invertible if and only if it has a set of linearly independent columns. What did we say about the determinant? I mean, what do we say about the volume of an end pipette? What would happen if one of the legs in the end pipette was linearly dependent on the others? It should give us a what? A volume of 0. So either the volume is 0 or it's not, right? Either the columns form a linearly independent set or they don't. And so if you think about this, what this suggests then is that the determinant of a matrix is non-zero if and only if what? If it's invertible. Because the determinant being 0 would indicate that there's a linear dependence amongst the columns of the matrix being determinated. Determinated, that's not really a word. You know what I meant though. So it worked, right? Okay. So this is huge. In other words, this, if and only if, the determinant of A is not equal to 0. Woohoo. That's kind of nice. So if you want to just check whether or not the determinant of a matrix exists, whether or not the inverse of a matrix exists, well, calculate the determinant. If you want to check whether a set of n vectors in n dimensions is linearly independent, put them together into a matrix, calculate the determinant. If it's non-zero, they're linearly independent. If it's 0, there's a linear dependence that you can find, right? Now, the determinant doesn't tell you what that linear dependence is, but it tells you it's there to find. That's very nice.
And is that why it's called determinant?
It determines many things, yes. So let me show you a few more things here. As you have noticed, actually writing out things about the determinant is a very laborious task, is it not? You've experienced it. So I would like to point out some things about calculating determinants that are very, very helpful. All right? First of all, the determinant of a diagonal matrix is just the product of diagonals. If you think about the geometric origin of the determinant, that's almost stupid. It's like the determinant of L0, 0W is length times width, right? Because the area of a rectangle with length L and width W is length times width. I mean, and so the determinant of a diagonal matrix being product of diagonals is really just the extension of the length width formula. So that's one thing. If you can get a matrix being diagonal, come on, you can do it. You can do it. You can do it. Ah, there we go. Once upon a time, I'll foolishly try to get, I'll get sucked into trying to reproduce this diagram in class. Never goes well. But you can actually, if you play with this a bit, you can see why the 2x2 determinant formula really does give you the area of the parallelogram given by like A1, this one being A1, A2, A11 words. I mean, you can actually see the area as being this if you sort through this picture. And for those of you who had Calculus 3, I actually derive the formula for the triple, remember that triple product formula we have? Well, if you look at that, that is exactly my definition of determinant in the 3x3 case, all right? So the generalization to the anti-symmetric symbol in Rn, it makes a lot of sense. But anyway, this is not what I was trying, I'm rehashing what I've already said. Let me go on. So here's, this is yet another way of writing the determinant. Mathematicians like this, if you can write it as a sum over permutations, all right? But an equivalent way of writing that is what I put on the board. Since you guys don't know what permutations are, I decided to focus my attention elsewhere. You'll learn about permutations in Math 421, okay? Here's the definition that I gave you. Here is the explicit, gory, stupid formulas for expansion across the top row for a 4x4 with the A, B, C, D, E, F, G, H, I, J, K elemental P matrix. Okay? There you go. And here's the A, B, C, D, E, F, G, H, I expansion of the determinant across the top row. And here's the thing you've already seen in the formula for the inverse of a 2x2 matrix. Remember, that was the denominator, which had to be non-zero, or else the matrix is not invertible. So, to quote the great Hannibal, I love it when a plan comes together. Now, this is the technical jibber-jabber behind the Laplace expansion. All right, the factors and cofactors and minors and all this good stuff. Sorry, I'm just backing up here a little bit. And you know, if I had a different audience, perhaps I'd make you guys prove these things. But this is the Laplace expansion by minor. The determinant can be written either as a row or a column expansion like so. And the actual proof of that, to really prove that you can get from my definition to Laplace's expansion by minors, it is technical. It looks like this. All right, there it is. You can look at it if you want or not. Another thing you prove in the context in the process of this is that the determinant of a matrix is equal to the determinant of the transpose of a matrix. In some sense, that says it doesn't matter if we look at the parallelogram as being indexed by row vectors or as by column vectors. It's the same volume. It shouldn't matter whether or not we look at the matrix in terms of rows or in terms of columns. Something like that. But anyway, a determinant, the matrix is invariant under transposition, another property of determinant. Super nice. Here's some examples with numbers. Another example with numbers. Another example with numbers. Properties of determinants. This is what I wanted to get to. All right, so like I was just telling you, the determinant of a matrix is equal to the determinant of the transpose. I gotta get some batteries for that one. This won't work. If you have a 0 row, the determinant's 0, right? That makes sense if you think about the geometric origin. The determinant also, now this is less obvious, but the determinant of a sum, it has this, we don't have linearity of the determinant. We've got like linearity with respect to one column. This ends up later being called multilinearity. So you can break up sums and pull out scalar multiples from a given column as long as everything else stays the same. And likewise for, you can do the same, it's also the same for rows. This is interesting. If we pull k out of the determinant, we pull out k to the n. Right? Think about that in terms of the application to the sign volume. It makes a lot of sense, right? If you scale both the length direction and the width direction of a rectangle by a constant, it multiplies the area not by a constant, by the constant squared. And here's some other things. Any row swap changes the sign of the determinant. This kind of row operation, which was type what? Type 3 was it for us? A type 3 row operation doesn't change the determinant at all. And if we do a row scaling, then it if any row is a multiple of another one, it's just 0. All right. So these can be used to calculate determinants and with great success. Like I told you, the determinant of a diagonal matrix is the product of the diagonals. It's also true for a lower or upper triangular matrix. If you have an upper triangular matrix, the determinant is just the product of the diagonals. Likewise for a lower triangular matrix. So if your matrix happens to be upper or lower triangular, determinant's super easy to calculate. There's also something to say about, I already told you this, right? A product. The determinant of a product is the product of the determinants. Don't take this formula lightly. It took me, if you read the notes, it takes the better part of 2 pages of careful calculation to prove this. This is not an easy thing to prove. And the way I prove it is it's immersed in basically proving the product rule for elementary matrices and then seeing that that allows you to transfer that fact to matrices, because matrices which are invertible can be written as a product of elementary matrices. On the other hand, if the matrix is not invertible, that means its determinant is 0. So this formula becomes true just in kind of a stupid sense. This is not an easy formula to derive, but you will use it. And last but not least, the determinant of a block matrix, block diagonal matrix like this, is the product of the determinants of the blocks. This is very, very useful. All right? And I am sure I have assigned you homework problems that are based on that. So here's a more insidious example. See what I do? I take this row and that row and I swap them. That changes the determinant by a minus. And with that simple row swap, I then have a diagonal matrix. So I just multiply the diagonals and get minus 48. Right. There's lots of computationally easy things I can ask you about determinants that are based on you understanding the properties of determinants, right? Now, everybody here should be able to work out like a 3x3 determinant with ugly numbers in it, right? I mean, that might happen to you, but you should also be aware of like this kind of sneaky stuff. So next time, I will talk to you guys about Cramer's rule and further things we know about determinants, all right? Thanks, guys. Yep.